Welcome learners to today's chemistry lesson. The teacher is Martin Bunguswa, and today I'm going to present to you organic chemistry, which is a continuation of alkenes that we had started on, and we continue with the chemical properties. Welcome. The first chemical property that we had discussed on the alkenes was the combustion, and we looked at combustion as one of the confirmatory tests that is used to test for unsaturation. Today we move on to the next type of a reaction, which is called an addition reaction. I want you to note that alkenes also undergo combustion. Alkenes undergo addition, but alkenes undergo substitution. In substitution, UV light is needed and you only use a halogen. But addition reactions are quite a number. So an addition reaction is one in which an unsaturated compound reacts to form saturated compound. And addition reactions of alkenes are named from the reagent used to cause or initiate an addition reaction. The first one is called hydrogenation. So hydrogenation is a type of an addition reaction. So hydrogenation is an addition reaction in which hydrogen, in presence of palladium or nickel catalysts at high temperature, react with an alkene, and during the reaction, an alkane is formed. Now, addition of hydrogen to an alkene has industrial application, and this industrial application is hardening of oils during manufacture of margarine, where the hydrogen is passed through liquid vegetable oil or animal oil at about 180 degrees Celsius in presence of nickel catalyst, and a solid fat is formed. That process is called hardening of oils. Now, if you look at the screen, I've given examples of those reactions of alkene with hydrogen. It's very easy to understand that when the hydrogen is added, remember it's called addition, meaning the one hydrogen adds on one side, the other hydrogen atom adds on the other side, and you get an alkane. In all addition reactions, an alkane must be formed. And the reaction, it takes place in presence of nickel catalyst heated to temperatures of about 180 degrees Celsius. If I add hydrogen to propene, I get propane. If I add hydrogen to butene, I get butane. If I add hydrogen to propene, I get propane. No other side product is formed. Unlike in alkanes where during substitution you must get an HCl or HBr or HI depending on what you added or what you substituted. But in the addition reaction, you only get a corresponding alkane. So addition of hydrogen to an alkene will give you a corresponding alkane. Next one is addition of a halogen, which is called halogenation. The halogens that can be added are either fluorine, chlorine, bromine, or iodine. Whenever a halogen is added, the double bond breaks and a single bond is formed. But the single bond that is formed is a compound which is called a haloalkane. Haloalkane means it is an alkane that contains a hydrogen atom. And when halogens are also used during the reactions, the color will fade. The color of the halogen will fade. If I use bromine, if I add bromine to ethene, the double bond breaks. One bromine atom goes on one side, the other one goes on the other side. I end up with a single bond. And I get a compound which is called 1,2-dibromoethane. And during the reaction, the bromine color will fade. Or the bromine gas. If I'm using bromine gas, then we say the color of bromine will be decolorized from brown. If I use chlorine water, it will be decolorized from yellow. So I can either use bromine, I can use chlorine, but note that it is just the same way we had written the others. It's simply the the double bond, the position of the double bond is the most reactive site for the reaction. That the double bond will break and the halogen will add itself across the double bonds to form single bonds. I can also add hydrogen halide. Hydrogen halide example is hydrogen chloride, hydrogen iodide, hydrogen bromide. In all the reactions, again, the double bond is the most reactive site. The hydrogen bromide atoms will surround the double bond and remove it there. And it just add itself. When one hydrogen goes on one carbon, the bromine goes on the other one. And I also get a compound with a single carbon. What you can see on the screen are those examples of addition reactions involving hydrogen halide. HBr, HCl, or hydrogen iodide. Bromine water is not the same as bromine. So when I talk about bromine, it's Br2. When I talk about bromine water, this is now the bromine that has been dissolved in water to give us a compound which is called HOBr. When you add bromine water to ethene, for example, you get what you call bromoethanol. Because the bromine atom goes on one carbon, then the OH goes to the other carbon, and you end up with what you call bromoethanol. But when I add bromine gas, I just get 1,2-dichloroethane. Another type of reaction that is undergone by alkenes is called oxidation. Alkenes are easily oxidized to alkanos with a dual or a double functional group by a suitable oxidizing agent. The notable oxidizing agents that can be used are either acidified potassium manganate 7 or acidified dichromate 6. These are the two common oxidizing agents. When you bubble ethene through acidified potassium manganate 7, the oxidizing agent supplies the oxygen and the alkene gets oxidized with a dual functional group, which in this case is the OH and the OH. Remember we said that oxidation of alcohols, of alkenes, produces alcohols. So when you oxidize ethene, as you can see there on the screen, it produces a compound which is called ethane 1,2-diol. It is called a diol because of the two OH groups. And it's 1,2 because the first one is on the first carbon, the second one is on the second carbon. Ethane 1,2-diol is also called glycol, which is commonly used as a coolant in motor vehicle radiators. Don't confuse between ethane 1,2-diol and glycerol. Glycerol has 3 OH groups, but ethane 1,2-diol has only 2. So when you oxidize ethene, you get ethane 1,2-diol. And the experiment is carried out using acidified permanganate or acidified dichromate 6. The other type is called hydrolysis. Hydrolysis is the reaction of a compound with water. Alkenes undergo hydrolysis to form alkanols. And this reaction takes place in 2 steps. First, the alkene reacts with the concentrated sulfuric 6 acid at room temperature to form a compound which is called alkyl hydrogen sulfate. And then on addition of water, the alkyl hydrogen sulfate is hydrolyzed to become an alcohol. And you can see on the screen that is now the equation for the reaction that is taking place. Ethene, which is CH2, I've put the structural formula of the alkene so that you can be able to see how the mechanism of the reaction is taking place. So we can say that hydrolysis reaction involves 2 steps, involves 2 reagents, concentrated sulfuric 6 acid and water. So when you add sulfuric acid to ethene, the first thing that happens is the sulfuric acid splits into a hydrogen and a hydrogen sulfate. Now the O of the hydrogen sulfate becomes attached to the carbon to give us a compound called ethyl hydrogen sulfate. As you can see here, this structure that you can see here. Then, now when I add the water ionizes to produce a hydrogen and the OH. Now the OH gets and replaces the hydrogen sulfate, and then sulfuric acid is regenerated in the whole process. So at our level, we may not require you so much to know about the ethyl hydrogen sulfate. However, you need just to know that hydrolysis of an alcohol, of an alkene, produces an alcohol. If I hydrolyze ethene, I get ethanol. Propene gives me propanol. Butene gives me butanol. And the reaction is called hydrolysis, although it takes place in two steps, where there is hydrolysis and hydration at the same time. If you recall, the way alkenes were prepared was by dehydration of alcohols. Now, when I hydrate an alkene, I now get the alcohol. So you can call the process as either hydrolysis or hydration because of the two steps that are involved during its formation. Now, that hydrolysis reaction can also be carried out using phosphoric acid and temperature of 300 degrees Celsius and a pressure of 60 atmospheres. That process can also be carried out using temperature, and you can also use steam. If I don't use sulfuric acid, I can also use steam and high pressure, so that the alkene quickly becomes converted to an alcohol. Although the main method of producing large quantities of ethanol is fermentation, but this one can also be used as a large-scale source of alcohols. The last type of chemical reaction undergone by alkenes is called self-addition, also called polymerization. When you do Organic 2, you're going to learn more about what polymerization involves. Now, polymerization, which is called self-addition or addition polymerization, is the process where a large unsaturated molecule, which is called a monomer, join together to form a large saturated molecule, which is called a polymer. So the two small units are called monomers, and the large continuous chain is called a polymer. Only alkenes undergo addition polymerization. It's important to note that alkenes do not. Now, the type of the polymer that is formed will depend on the monomer. Now, during addition polymerization, the double bond of the alkene will break, free radicals are formed, and the free radicals collide with each other and join to form a large molecule. Now, during addition polymerization, we need temperature of between 350 to 450 degrees Celsius. We need pressure of 35 to 40 atmospheres. And we also need a catalyst, which is called Ziegler-Natta. Those are the three conditions for addition polymerization to take place. I want to show you a case study of polyethylene. Ethene is a small molecule. Another ethene is a small molecule. So ethene combines with ethene many times. And the end product is a long chain molecule, which is called polyethylene. Because it's very long. So that's why it's called poly. If there were two, it could have been called dimer, but now this one is polymer. So this is a way we represent a polymer. You can see it on the screen. I draw carbon, 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 carbon continuous like that, but on the end, I leave it as an extension. we leave it as an open chain to show the extension of the molecules on either side. And what you can see on the screen are how many repeat units. You count like this. This is 1, 2, 3. There are 4 repeat units in that particular structure. But when I draw the one that you can see down there, this is one showing what you call a repeat unit. And when I draw one repeat unit, I put an N. The N tells you that this structure can repeat itself n number of times. Now I want you to know the difference between a monomer, a polymer, and many repeat units. This structure you can see C with a double bond, C with a double bond. This is called a monomer. And this one is the structural formula of a repeat unit. But this one is showing 4 repeat units. So when you're showing more than 1 repeat units, you do not put N. But when you're only showing 1 repeat unit, you put an N. And the number of monomers forming that particular polymer can easily be calculated using the example that you can see on my screen. For example, polyethylene has a molar mass of 4,760. Calculate the number of ethylene molecules in the polymer. So what I do here, I calculate the molar mass of the molecule, the repeat unit, C2H4, which is 28. Then I say 28 into N, because I'm taking carbon 12 plus carbon 12 plus 4 hydrogens into N is that amount, 4760. What is N alone? And I get 170. So it is not practical for you to draw 170 molecules on a piece of paper. But now we can be able to tell that one molecule, one polymer of polyethylene is made up of 170 ethylene molecules. When you go to organic 2, we shall learn more about other polymers. This one we had to mention because it's one of the properties that alkenes undergo. Then polyethylenes, commonly known as polyethylene paper, used to make plastic bags, used to make balls, used to make packaging or materials, and other essential materials that are made from plastics. What is the test for alkenes? Chemical test. One is they all burn with yellow sooty flame. That confirms presence of double bond. 2, they decolorize acidified manganate 7. That one is also another test for double bond. Another one is they all decolorize bromine water from yellow. So those 3 can be used as chemical tests for double bond structure. What are some of the uses of ethene? 1, ethene is used in the manufacture of plastics like polyethylene. It can be hydrolyzed to produce ethanol. Ethene can be used in ripening of fruits like bananas. And ethene can also be used in manufacture of some detergents. Now, unlike the alkenes, we like summarizing the properties of alkenes using a flow diagram. Because when it comes in the exam, it is always important to know which are these processes. Like you can see up here, this is called polymerization. This is called addition of bromine, we get that. This is called addition of chlorine, these are the products. This addition of hydrogen halide, this addition of hydrogen, this one is called combustion. So later on, we shall be looking at a more octopus way of analyzing a particular flowchart so that it incorporates all its properties. Like you look at this flowchart, I'm here to put the hydrolysis. We shall also insert. You also insert another process which is called oxidation. So this is just a summary of the processes that alkenes undergo. The next homologous series is called the alkynes. So alkynes are hydrocarbons that have a general formula of CnH2n-2. And they have a functional group of carbon to carbon triple bond, as you can see on the screen. The first member of the alkyne family is where N is 2, because carbon 1 does not exist in nature. And where there N is 2, then when we substitute in that formula, then it becomes CH triple bond CH, and the name is called ethine. When N is 3, remember we don't have N is 1. When N is 3, that is the second member, and the structure is as shown on the screen, and that compound is called propyne. It doesn't matter where the methyl group appears. It can appear on the right, it can appear on the left, there is no problem. The next one is butane. You can see there are 4 carbon atoms, and the triple bond is on the first carbon. And it's always important to emphasize on the position by calling it a 1. But1. But1 means the double bond is on the triple bond is on the first carbon. Prop1 means the triple bond is on the first carbon, etc. This one is called pent1. Pent1, there are 5 carbon atoms, and the triple bond is on the first carbon. Then I have hex1, where the triple bond is on the first carbon, as you can see the structures on our screen. We always encourage you to keep practicing on how to draw the structural formulas of all these compounds. But remember, once you understand the alkenes and the alkenes, it's also very easy for you to understand these structures. And when you'll be drawing the structures, always remember that every carbon atom must be surrounded by 4 bonds. So it's just automatic that they just fit directly. Alkynes also form a homologous series in which carbon atoms have triple bond, and they are also called unsaturated hydrocarbons, because every carbon atom does not contain a maximum number of hydrogens. Isomerism also occurs to alkynes. Just like alkanes and alkenes, alkynes also exhibit isomerism. And the rules of naming isomers in alkynes are the same basic rules or guidelines that we use to name isomers in alkenes. You identify the longest continuous carbon chain that contains the carbon-carbon triple bond and determine the parent alkene. Then you number the carbon longest chain from the end closer to the triple bond. For alkenes, we number from the end closer to the double bond. For alkenes, we number from the end closer to the methyl group. But now for this one, we number from the end closer to the triple bond. So, I'll not overemphasize on the naming of alkynes. We shall give you examples. We want you to go and draw the isomers of butane and pentane. They just take the same format as the one for alkenes and alkenes. How are alkynes prepared in the laboratory? Alkynes are prepared, but now when we talk about alkynes here, we are being specific. We are only going to prepare ethine. Ethine is prepared in the lab by reaction between water and calcium carbide. Remember, when we discussed about preparation of gases, ethine was one of the gases where we say it can be prepared by reaction between water and calcium carbide. And the reaction is highly exothermic. And if you look at the setup on the screen, this is the setup that is used to prepare the alkyne, the ethine. There is calcium carbide mixed with sand. Then water is added from the dropping funnel. The reason why we are using the sand is because the reaction is highly exothermic. And therefore, this sand is put above the calcium carbide to absorb excess heat. To absorb excess heat and prevent the flask from breaking. And copper 2 sulfate can be used as a catalyst in this particular reaction. And it is collected over water, because it is slightly soluble in water. The accompanying equation for the reaction is calcium carbide plus water gives you calcium hydroxide plus ethane. And if the reaction was to take place for a very long time, then you can explain why there will be formation of a wet precipitate. And the properties, the physical properties of alkynes are exactly the same physical properties of alkenes and alkenes. They are also colorless liquids, gases, either solids or liquid, not poisonous, and slightly soluble in water, and the solubility decreases as you move down the homologous series. And those properties are summarized in the table that you can see on the screen. So in our next lesson, we are going to cover the chemical properties of alkynes. So the assignment for now, you go and draw the isomers of alkynes so that it becomes continuous with the alkenes.